Okay, we are ready to start looking at module number 7. So I'm going to go over to our modules. This is our second to last module in the course. And in this module, we're going to be introducing really our final, if you would, subject. But for the next 2 weeks, we'll be working on reinforcing it. And it's going to be assembly drawings. I'll kind of add that as a header there. So if we look at I still have it broken up into 1 and 2 sections or sessions, but they're really going to kind of blend together. We're going to get started on session 2 today as well. But we're going to be looking at our tech drafting textbook, and chapter 14 in our tech drafting textbook is going to be really kind of going over the rules and how to set up assembly drawings and all that kind of stuff. So we'll be looking at that in a little bit. And then you're also going to notice, if I go back to my module 7, you're going to notice here that I do have 2 assignments out here. Okay, 2 assignments out here. The first assignment is what we're going to be getting started on, and I'm going to explain to you at the beginning of class here. Okay, so let's take a peek at module 7 assignment, shaft support revisions. So if we click there, you're going to notice that there are 3 drawings for you to download. Okay, 3 drawings for you to download. And what you're going to do is you're going to update these. Now, a very common practice when you're out in industry is you're going to have to revise existing drawings. Okay, so that means you're going to have to pull up somebody else's stuff, make some revisions to it, record the level of revision. We'll talk about that in a little bit, and then resave it, and then it's updated. So I want you to go through that process with the 3 drawings that I have out there right now. Okay, so if you want to go ahead and download those, go ahead. I'm going to give you a little bit of time to do that, about maybe two minutes. And then in the background here, I'm going to kind of pull mine up as well in AutoCAD. And I would suggest pulling up all 3 in AutoCAD so that you have them available as tabs, so you can kind of easily switch between. So if you go back to module number 7, download each one of these, whether it's, to a local drive or probably a jump drive if you're here in class, and then have those available so you can pull them up in AutoCAD and you can be, seeing what I'm seeing. Now we're going to be working with these files as really kind of our first assembly. So once we do the work we need to here for the revisions, you're going to notice that there is a second assignment out there for module number 7. And that is going to be creating the subassembly, okay, with these 3 parts and additionally a fastener. And that's going to be our AutoCAD work. But right now, just do the revisions. We're going to do the revisions, and then we're going to, I'm going to show you that process. Okay. Matthew, I saw that you just came in. Please go to module number 7 assignment and download the 3 files that are in the shaft support revisions assignment. We're going to be working with those. Okay, now I can only gauge what's in my room right now, so I'm going to assume that most everybody has these downloaded. You look like you're kind of waiting for me. So what I want to do is I want to go through and show you what's going on each one of those drawings. But before, we're just gonna go underneath my camera here briefly. So what I did was I printed out and got physical forms of each one of those drawings, and I want to do this for a couple of reasons. Number one, you'll notice that when I print these out, certain lines are thicker than others, because when I plot it or I print it, what's going to happen is it's going to follow the line width that we set up in our layers. That's why it's important to have the layers set up. So when I print something off in black and white, for instance, now I can see that my object lines are thicker, my center lines and my hidden lines are less thick, as well as any hatching that I have here. So So basically, I just wanted to kind of show you why it's important to have everything set up properly so that the line weights come through as well, and it's an easier drawing to look at. Okay, so the first drawing that I have up here is the collar. Okay, have everything filled out, and then you'll notice that up in the top here, I want you to update this to specify an RC3 fit to mate with the bearing. Okay, and then part number two here says add a revision to this drawing documenting this change. So what you're going to do is you're going to update this dimension right here to fit properly with the bearing. So the bearing, if I look, is on my next page here. Okay, and this collar is going to fit right into the top here. Okay, now right now the way it's dimensioned, it's 2 inches here and it's 2 inches here. So this part right here is going to sit down in there. Okay, and if you go to the very beginning of chapter 12, this is going to be the assembly that we're going to be working on. Okay, these 3 parts are going to be part of that, and then in addition it's going to be the 2 screws on the sides. So this is our collar and this is that bearing, and we want it to sit down in here so that it can sit properly. Now, if for instance we make this to the dimensions we have here, we're going to have problems. So what I want you to do right now is on this 2-inch dimension on our collar and on the 2-inch dimension on the 2-inch dimension on our bearing, I want you to write out, based on the title block tolerances, write on a piece of paper on notes, write out what the high and the low values would be for each. Okay, I didn't do the drawings. I didn't print them out because I'm finding that nobody really takes some of the left behind. So I'm just gonna go with it. So what I want you to do is take each one of these dimensions, the 2-inch dimensions, the 2 that we're interested in, and I want to know what my min and my max value are, and then make sure that you look to the title block for what those values would be. Okay, so just go ahead and just write it down. So one would be for the collar and one would be for the bearing. Everybody should be writing down what these values are. If you're doing other things, then you're risking not getting the information because you're going to be handing something in associated with what we're doing here. So, so it's your choice if you want to follow along or not. But if you don't do it, you know, in the way that's required, then unfortunately, then you'll have to redo it and rewatch videos and stuff like that. You're here now. Okay. So I'm going to look at the collar first. What would be my maximum value for this 2-inch dimension, defaulting its tolerance to the title block, James? 2.02. Yep, 2.02. Okay. And what is going to be my minimum value here, Christian? 1.98. Okay. So that's on my collar. Now I'm going to go over to the counter bore. All right. So the counter bore, what's my max value on that 2-inch dimension? 2.02, and then my min is going to be 1.98. It's exactly the same, right? Now, what is happening here is not uncommon. A lot of times when people don't understand tolerances or they haven't been trained properly in how to help things come together and design them, what ends up happening is they're like, oh, I'm going to make that 2 inches. So for it to fit into, I have to make the whole 2 inches. All right. Unfortunately, that's not going to work. And why isn't it going to work? Why isn't it going to work? Tell me. James. They could be machined perfectly properly. And what? There's going to be some that aren't going to fit together, right? There are. Why is that? Why is that? So for instance, if I look over here, my largest my largest, I'm going to call this my shaft, okay, because this is like the outside, the external feature of this, right? I'm going to call my largest shaft 2.02 is larger than the smallest hole. I have a problem there. I have a problem. If I make this to its largest size and I make this to its smallest size, they are not going to fit together, but they would have been made exactly the way that I would have put it out there. The machinist wouldn't be wrong. Anybody who was associated with making these parts wouldn't be wrong. Who's wrong? Who didn't think ahead? The designer, the designer. That's why each and every one of these dimensions, it's not about just what size it is. It's now going to be, as we look to the next subject, the last subject of this class, how are we going to fit these things together? Okay. And that actually is going to be proof in the pudding how you did your design job. Okay. When the parts get out on the shop floor and they're assembling them and there's a lot of questions and things aren't happening and they're not going together, they're going right back to these drawings and they're going to say, well, they were made to the print. They were made to the print. But yeah, the designer didn't take the time to figure these out. Okay. So when we have parts that are going to be fitting relative to one another, worst case scenario doesn't work. Exactly, Josh. Thank you. Unfortunately, now it's going to be on the designer. Now it's going to be on the designer. So for instance, maybe this happened. We got these out there. They were made to print and they didn't work. So now we need to actually specify a proper fit here and make a revision to this drawing. And that's the process you're going to go through for this feature. Okay, so I'm going to walk you through this. An RC3 fit. We talked a little bit about fits last time, but I told you we're going to get opportunities to look at these. And this is our first one. So what we want to do is we want this to be what we call a running clearance fit, meaning that every single time these two go together, they come together no matter what. When the collar is made, when the bearing is made, they are always going to fit together. So now I have to figure out limits here, min and max, and limits here, min and max, that are going to allow that to happen. And there are tables that help us with that. Okay. So what we're going to do is we're going to be looking at these in this particular case, an RC3 fit. So in the back of your book, and this is going to be your tech drafting textbook in the appendix. That's where we're looking. So get your big, heavy book out. If you brought it, you should be bringing, I know it's a big book to bring back and forth, and it's a lot to lug around, but we're going to continue to be opening this book up and using it in multiple classes throughout our time together. Okay. So I'll let you get here. So we're going to open up to appendices A38. A38. And if somebody doesn't have their book next to you, please share your book with them so that they can get a view of what we're looking at. Okay, so this is going to be our first kind of shot at this, if you would. All right, we haven't really formally gone through this process yet, and that's okay. And that's why I want you following along, because you're going to be making these changes to the drawing, and this is going to be what you're going to be handing in the assignment. Okay, so we're going to do it together. Basically, you just have to hand in the files. Not a big deal. All right, so now you'll notice that right now I've got clearance locational, okay, and I'm going to go back. I'm sorry, not 3.8. I want it to be actually on 36, A36. We're going to go back to the very first one here. This is running clearance fits. Now, before we go into the chart here, you're going to notice that we have an RC3. That's what we're going to be focusing on for our problem. But I want to just kind of explain a couple of things here. First of all, these are standard types of fits that have already been specified for us, meaning they've been already figured out. So the numbers in the chart here are going to be how we're going to be applying the numbers in the tolerances. Okay. Now, there are a couple different types of fit depending on the type of application you have. Bless you. So you as the designer are going to be the person that's going to know best, how these are going to fit together and what the appropriate tolerance is going to be. And this is kind of like, at first it's going to be, based on the descriptions that you read and try to match it up. As you move along in your design career, there's going to be more and it's going to be easier for you to be like, oh, it's this kind of a fit or that kind of a fit. Okay. So the first big overarching type of fit is running clearance. And what that means is every time I put them together, they're easily going to go together. And there's even going to be a little bit of slop or a little bit of what we call allowance, positive allowance between them. Okay. And so they go from RC1 and they continue all the way to RC9. Now, to know which one would apply for you, you're going to notice that at the top here, there's a description for each one. Okay. So when we look at an RC, for instance, 1 fit, this is intended for accurate locational parts. Okay. And then if we go to the other end of the spectrum and we go to an RC9 fit, this is going to be very loose running fits. Okay. So the RC9 has, if you would, the most amount of clearance or a positive allowance. And over here at the RC1, this is going to be less. Okay, more accurate type of a location. And then you'll notice as we go from 2 to 3 to 4, it continues to kind of, gradient and go back and forth between that scale. Okay. We're going to turn the page to 38. This is called clearance locational fits. These are LC fits. There are LC1 all the way to, on the next page, LC11s. And they work exactly the same way. The ones are going to be the most accurate and the 11s are going to be the least accurate. Now, these are, as a class, a closer clearance fit than what our running clearance fit is. Because so the running clearance fits are kind of like, we just want 2 things to go together. Locational start to get into more accurate, where we're going to be working with things that we don't want to maybe compress too much. Okay. And we want to make sure that there's a nice fit, but they're almost going to go together practically line to line. Okay. And they're going to slide nice and even together. And these tolerances are going to be like 4 or 5 decimal places. Okay. Then we have transitional. So this is another next level locational type of a fit. This is going to be what we apply to, for instance, dowel hole pins. Dowel pins are usually used for locational purposes, and we don't want those to move around a lot. And there's going to be a little bit of press in there. So locational is almost like line to line contact and a little bit above and a little bit below. So it's kind of like tapping your piece in. Okay. And those run from an LT1 to an LT6. Again, this is going to be your closest and this is going to be your sloppiest, if you would, but they're not going to be very sloppy at all. Okay. And then trying to think, yes, we got 2 more. Interference fit. Interference locational fit is now going to be, we're always going to have to press them together in some way, shape, or form, whether it's tapping or pressing with a press. Okay. And again, LN1 to LN3. And then as we turn the page, now we're going to get into the force and shrink fits. This is pounding, pressing them together, and or heating one up, cooling one down, putting them together and letting them, kind of settle in on an ambient temperature. And now they're going to stick together. They're not coming apart. Okay. Unless you kind of destroy them, if you would. Okay. So that's kind of like all the different types of fits that we have. Now, the nice thing about these charts, and these charts are, you can find them in what we call the Machinery's Handbook. I don't know if any of you have ever heard of this book before, but the Machinery's Handbook, I'll put it underneath here. The Machinery's Handbook is this really thick, and I am not familiar with the program enough yet to know if at some point you buy this in the program. I know at the previous college I was at, the other program, we did have students buy it at a certain point. But the Machinery's Handbook, you're going to kind of notice here, it's like super thick. And it's kind of like, if you would, the Bible for mechanical design and machining, manufacturing types of operations. Okay, not just machining. And the nice things about this is there's a lot of standards in here, and all of these charts are there as well. So this is based off of the accepted standard. And then this is a place where you would also see it published. Okay. You could do a search on these things as well, and you should have pretty good numbers, but it's always good to use a verified source. So it being in our textbook and or Machinery's Handbook are 2 great places to do that. Okay. So let's go back to the chart that we're going to be looking at. And as we practice using this and applying it to the numbers that we have, this same process is going to be practiced for each one of these levels of tolerancing. Okay. So we picked, and I said, I told you guys, you're going to use an RC3 fit. Okay. So we find our RC3, first of all, chart, and then our column. Okay. Now this column has 1, 2, 3 columns inside of it. Okay. The first one is going to be limits of clearance. And then you're going to notice that there's a subheading over the top, and then there's going to be the hole, and there's going to be the shaft. Now the H7 and the F6, don't really worry about that. All right. Now, the other thing about this chart is that all of these are based on what we call the basic hole system, meaning, actually, you guys tell me, what is the basic hole system? We talked about it. You guys had an assignment associated with it. Do you remember what the basic hole system was? There was basic hole system, basic shaft system. I know we just talked about it once. You may or may not. You're like, I kind of remember hearing about it. I think I remember talking about it, but I don't remember exactly what it is. That's okay. What it is we have our basic size on the hole. Okay, in this case. And can you tell me, do you remember the reason why the basic size is on the hole? So for instance, if I have a 1/2 inch diameter hole and then a 1/2 inch diameter nominal size shaft, the basic hole, that nominal size, is going to be on the hole. Why is that? Do you remember the reason why? Anyone? When you make that hole, what do you make it with? If it's a 1/2 inch hole, I'm going to probably pull out a what? What size drill? A 1/4 inch drill? A 1/2 inch drill. It's made to that size. Okay. So that's why we normally, I'm going to say 95, 98% of our tolerances are going to be based on the basic hole system. And that's how these charts are set up. Okay. Meaning that the basic size is going to be on the hole. You're going to find, if, like I said, if it's a 1/2 inch diameter hole, 1/2 inch diameter shaft nominally, that 1/2 inch diameter is going to remain on the hole, and it won't be on the shaft. And it won't be on the shaft because when we create it on the shaft on a lathe, all we have to do is move that tool in a little bit, and we can just take more material out, and we can customize that size more and more easily than we can on the hole size. On the hole size, we have to then go into, maybe boring it out or reaming it out. And it's just extra operations to try to get to a special size, if you would, rather than going with what the tool is. Okay. Just going to check my little chat here. Easy to remove material. Absolutely. Thank you. Thank you, Josh. You got it. You got it. All right. So, so now let's look at this, look at this chart and see how this works. So first of all, the limits are in thousandths of an inch, thousandths of an inch. So that means that I have a decimal place of 0.00 and then my number. Okay. And then my number. So when I look down here, I'm going to start it on the first row here. Notice that all of my values are 0.3, 0.95, 0.4. That's not 0.4 inches. That's 0.4 of a thousandth of an inch. So that means for every one of these decimals, we're moving it to the left 1, 2, 3. Okay, so let's see how that works. Clean piece of paper here. All right. So I'm going to go on this. I'm going to go on this top line, and in this case, you'll notice that over on the left-hand side, our size range is 0 to 0.12. So let's say that our diameter, our nominal diameter, is 0.1. Okay, 0.1. That's our nominal. So we run into that size. So over here, this is now going to give us, we're going to go right to the hole. So I have a hole and a shaft that are going to go together, and their nominal size is 0.1. So for the hole, I'm going to take 0.1, and for my maximum value, I'm going to go plus. Now, this is a thousandth of an inch, so this is 0.4. This is 0.4. So I'm going to go down here. 0.4 on my chart means I'm going to take this and I'm going to go 1, 2, 3 to the left, because this is in thousandths of an inch. That means I'm going to have 1, 2, 3 zeros. Okay. Every one of the dimensions in every one of these charts is to the thousandth of an inch. So we have to move that decimal place 3 places to the left, or divide that number by 1,000 is what we do. It's 1,000. So now that means that my plus is going to be 0.0004. Do you see that? Not 0.4, not 0.4 of an inch. It's 0.4 of a thousandth of an inch. Okay. Or we would say 4/10 of a thousandth. Okay. Questions there? Does that make sense? All right. Now we're going to do the same thing for The lower level, it says, oh, -0. Okay, so that means I'm going to go -0, 0, 0, 0. So now my limits are going to be doing this math. Okay, it's not hard. So that means I'm going to be, my maximum value is going to be 0.1004. And my minimum value for my hole is going to be 0.1000, right? Here are my limits, my high and my low. This is what you would put onto your drawing, okay? We like to put limits when they're, especially, they're very critical like this. So when we're trying to get a dimension, you can notice this here, to 0.0004, it's going to take a little time. It's going to take a little time, okay? Now let's do the shaft side, okay? So I'm going to put a little wavy line in between. We're going to do that very same thing, but now we're going to use the second column, okay? So our shaft, okay, is going to be equal to 0.1. And now on the top side here, we're going to say, oh, minus 0.0003. So to get that number, it would have been 0.3. And we go 1, 2, 3 to the left. So there's 1, 2, 3 zeros. Okay. And then we're going to subtract 0.00055. That goes to a fifth decimal place. So again, 0.55, 1, 2, 3, 1, 2, 3 zeros. Make sense? Okay, now let's do our limits over here. Okay, so now you guys are gonna have to do the math for me. If I take 0.1 and I subtract 0.0003, what do I get? I don't think it's 0.99, 0.0997. Is that right? Like that? Okay. All right. And then what's the number down below? I take 0.1 and I subtract 0.00055. What's my number? Everybody should have it. Be working on it. Gosh, it's boring if you watch everybody do it. I know. It's way more fun when you get to press the buttons. Everybody. Yes. Get out a calculator. I'm not trusting anybody's head. I don't trust my head. I'm not going to trust yours. I'm so sorry. Get out a calculator. I bet you have one on you somewhere. It might even be in the form of a phone. 0.0995 or 45? 45. That's okay. That's all right. Yep. 45. Now, you'll notice that we have a dimension. One of them is 5 decimal places and one of them is 4. When you put them on your drawing, they have to be to the same decimal. Okay. So you need to add a 0 or take one of them off. Okay. That's the decision as a designer you have to make. Whenever I put limits on a drawing, they have to be to the same number. And you're going to notice in AutoCAD, you can only set them up to one decimal place. Okay. And then you're gonna have to put your pluses and minuses in there. All right. So just know that that's the case. You have to have the same number of decimal places on your limits. Okay. So now let's do this very same process, but for the numbers we're going to be putting onto our drawing. Okay. So I'm going to turn this over and we're going to find down our column our 2-inch dimensions. So notice it goes to 1.97 and then it starts at 1.97. So I'm going to go along this row right here, right? Along this row. Okay. And then I'm going to go to my RC3 section. And now for my hole and my shaft, go ahead and write these out for the hole in the shaft and see if you can get them. And then we'll compare answers in just a bit. Okay. So it's going to be a diameter of 2 inches. And then you're going to apply each one of these tolerances. Make sure that you move that decimal place 3 places to the left for each one of these, and then add or subtract as it tells you. 1 for the hole, 1 for the shaft. So you're going to have min and max for the hole, min and max for the shaft. And again, this book we will be continuing to use in classes throughout the program. So this is going to be one that's going to be pretty worn out after you're done. So in Creo next term or in fall 2, if you're following along with the parametric CAD, we'll be using it in there as well. We're actually going to be doing a lot of models out of here for it. So so continue to bring it and keep track of it. You don't want to not have it. And I found that if you try to use a previous version, number one, the chapters have changed, but then we even found a mistake, not really a mistake, but numbers change in the models too. Even if they're called the same thing and they're the same numbers, the actual dimensions and the sizes, we found a difference or two. So, so get the most current version that we're using. Okay, let's look at our whole. So our 2-inch here. Okay, I'll add a couple decimal places to it, 4 decimal places. And now we're going to add plus 0.0012, right? 1, 2, 3. That means there's going to be 2 zeros in front of it. Do you guys agree? Okay. And then we're going to do a minus 0. Okay. So now with those numbers, that means that my limits are going to be 2.0012 for the maximum value and 2.0000 for my minimum number. Now, can I still use a 2-inch drill? What happens if that drill gets dull? Won't that hole get smaller? I mean, over time, if it wears away and it gets dull, won't that hole get smaller as I make it? Ask Brad. Ask Brad. You guys have Brad for manufacturing processes, right? What ends up happening is that the behavior of a drill is that the hole is actually going to get a little bit larger. Okay, so we'll still be okay, and that's why these are sized this way. Okay, as a drill dulls, what happens with the chips on the inside is they actually get like chunkier, and as they try to come out, they actually bore out that hole a little bit more. So I know it's not intuitive that that would happen. You would think as it wears away, that dull physically gets shorter or smaller, and it does. But because of the nature of the cuts not being as sharp and as accurate, the hole actually gets larger when a drill dulls. Okay, it's interesting. So so that's why we have it on like this. Our 2-inch dimension is our smallest value, and then it's only going to grow from there, if you would. Okay, so now let's do the shaft, right? So this was the hole. Now let's do the shaft, okay? So we've got our 2 inches, 2.000. This time we're going to be a minus 1.2 thousandths. So that means that we're going to be minus 0.0012 and a minus 0.0019. Do you see that? So it was here, 1, 2, 3. Oopsie, I'm sorry. Decimal place was here, 1, 2, 3 to the left. Those are the actual numbers that we apply. So now when I do this math, now I need your help. This is going to be 1 point. What is my number? Go ahead. 9988. Okay. And then this is 1.981. Okay. And that's going to be my shaft. Now we can easily see here, especially because of that 2-inch being the smallest value on our hole, we can easily see that no matter what size, and as long as I make my shaft within the tolerances that are specified and my hole within the tolerances, they will always go together with a gap, right? Right? Because my largest shaft is smaller than my smallest hole, right? There's always going to be a little bit in between there. And then if we look at the, where is it? Right here. If we look at the limits of clearance here, notice that the value is positive. They're telling us how much. What is the maximum amount of clearance? This is going to be 1/1000th of an inch. Because we're going to take 1, 2, 3 to the left. So 1/1000th of an inch. And our max is going to be 2.6 thousandths of an inch. That what occurs there is when I have my largest hole and my smallest shaft. It's the difference between those two values. So they're giving us like how good our fit is and how bad it can be, or how much slop, right? So questions on using the chart, pretty straightforward, right? Now, these are the numbers that we want to keep track of, because these are the ones that we're going to apply to the 2 drawings. Okay, so let's go back to the 2 drawings. Okay. Now, I am gonna, sorry, I grab my eraser. I'm gonna erase now. These two values that I have there, and I'm gonna replace them with the numbers we just got. Now, on my collar, am I a shaft or am I a hole here? I gotta know. That's the shaft. How do I know? Yep. It's an external feature, right? This is considered our shaft, even if it's not like long, like we would expect a shaft to be. It's a shaft dimension. So you are correct. This is going to be our shaft. And when we look at our bearing, I'm going to get rid of these. This is going to be our hole, okay? Because it's a counterbore hole. So, you know, it doesn't really depend. It doesn't really matter which one we're going to use, first or second. So we're going to apply to the shaft these values. So now instead of the 2-inch diameter, we're instead going to add, and I'm going to kind of put this at an angle so I can get it in here, 1.9988 to, the diameter needs to be in the middle, 1.9981, okay? And that is going to be what we're going to be changing that dimension to. Okay, this is a revision level we're making. Like I said earlier, somebody dimensioned it so that those values were the same. Now there was a problem in production and things aren't going together. So now we have to actually, you know, put a proper tolerance on here. And we chose the RC3 fit. Okay, and then we're going to go over to the bearing and we're going to put the hole numbers on this one. Okay, so this one, instead of that, I'm not going to get them in there. I'll go like this. This is going to be a diameter of 2.0012 to 2.0000. Okay. And I have to add those using AutoCAD. Okay. And we have that experience. So this is not redrawing this whole drawing. This is just making these changes. Okay. This is making these changes. Yes.
So are we actually like physically taking the section of part that's being measured and changing it, or are we just changing the dimension?
We're just going to change the dimension and we're going to apply the allowances there, because even, you know, in this one, we have our nominal dimension here. And as I told you, we always want to kind of draw on our nominal dimension first and foremost, right? And then apply whatever tolerances are going to be there. Sometimes our nominal is in the middle, sometimes it's not. And then here, since this is nominally, it's still nominally a 2-inch dimension. So having it at the 2 inches is okay, but then we're gonna apply the tolerance as a minus and a minus. Okay, and then the dimension will come out correctly. So you won't have to redraw this one. Okay. So the other part of this is number 2, for each one of these, add a revision to the drawing to document this change. Okay, again, this is what you have to do out in industry, because they have to see, okay, previous to this date, these parts were made to this dimension. So if we end up having problems, we know why. Okay, so so we need to put a revision level on here. Now, right underneath here, shouldn't have put this here for this drawing, but right underneath here, you're going to notice that that's where we're going to put our revision. Okay, whenever we do revisions, they're going to be letter callouts with a circle around them, and they are going to start with the first letter of the alphabet. So we don't start in the middle of the alphabet with a revision level. We say, okay, the first revision on a drawing is going to be letter A, then B, then C, and so on. Okay, so this is going to be revision level A. So I'm going to put an A with a circle next to it. Now all this is going to be horizontal and nice on here. I'm just kind of marking it up for right now. And then what we're going to do is we're going to add this revision level up here. Now we're going to extend the lines down. Okay. And I'll kind of show you what it looks like, but you will actually do this work. You're going to extend these lines down. And then underneath here in the revision, you're going to add A, not with a circle. You're just going to say, this is revision A. And then in the description portion, okay, because you have the A next to the new dimension, you're simply going to put was 2-inch diameter. And that's it. Okay. And then you're going to add, so that's going to go down in the description, and then you're going to add the date, whatever that is. Okay. And that's it. And now you save it with the revision level on. So your job is going to be, as your assignment, and I'll show you kind of the final version, what it looks like, is going to be to update the tolerance, put a revision level on it, and then add the description of what you did. That's going to be on the collar. And it's also going to be on your bearing, okay, for that part. So this one is going to be a revision level A. Okay. And then you're going to be doing that very same thing up here. Now, on the bearing, there's a little bit more work to do. So you'll notice down here, updates that you need to do. The first one we already did, specify an RC3 fit. Okay, we did that one. The next one is specify a depth on the 2-inch diameter counterbore to always seat the collar on the face. Here again, notice that we have a depth of counterbore, that's this dimension right here, of 1/4 inch. And then again, we've got a 1/4 inch here. Do you see how that could be a problem at times? Meaning this is not going to sit. And when I say on the surface, it's this surface we want to sit so that it always sits down on this surface right here. This could be made too long, or it could be made, I'm not going to say too long. It's going to be made at the high point of this tolerance, you know, down here. And then this could be made short within the tolerance. And now we don't have contact on that surface. So your job is to figure out what is a dimension that I need to change this to in order to make sure that I always sit here. Okay. And it could be changing this dimension, or it could be changing this one, or both. I don't know. I'm gonna leave that one up to you. This one's a little bit more wide open. We don't use the RC fits with this one. This one, you just have to look at the min and the maxes, that they don't interfere with one another. Okay. All right. So, so you have to do that. So that's going to be number 2 there. That's number 2. The third thing you do on this drawing is going to be specified the standard through hole size for a counterbore diameter. And that's these right here. And this is the through hole size. It's this one right here for the counterbore diameters, so that it's going to accommodate a 0.375 inch fastener specified in the shaft support subassembly. Okay, now this is that chapter 12 in your AutoCAD book. So right at the beginning of that chapter 12, you'll notice that they have a little drawing of a fastener. That is the fastener that is going to go through those 2 holes. Okay, now if we look at the body of that fastener, it's a fractional dimension. It's 3/8 of an inch. Okay. Now let's look at the through diameter. 3/8 of an inch. That's a problem, right? And remember, the last time we were together, we learned about standard clearance hole sizes. You had to fill them out, remember? And how much was that? Do you remember? What was the standard clearance hole size in that last column that you filled out on that sheet, that worksheet? Go ahead. Plus a 32nd of an inch. Yeah. So that's the standard clearance hole size. So all you need to do is go, okay, 3/8 of an inch is however many. Is it 4 32nds? No, 12 32nds. 3/8, 1/8 is 4 32nds. 3/8 would be 12 32nds. So 12 32nds plus 1 32nd is what? 13 32nds. But we're not going to put a fractional dimension on here. We're going to put a decimal dimension on there. So you need to change this to plus 1 32nd of an inch on the diameter. Okay. The counterbore is fine because you'll notice that the counterbore will accommodate what's there. All right. Because this counterbore is 9/16 and this is 5/8. So that's plenty. That's going to be step number 3. So you're going to update. Now this one, you need to draw the hole to the new diameter. Okay. Over here and over here. I'm going to check that because you're going to be handing in the files. And you need to do that because this is a diameter dimension. And it's first and foremost, it's a dimension based on the diameter that you selected. Okay. And you selected the inside one. And now what you're gonna, or it was selected, you didn't do it, I drew it, right? And I selected the inside as a diameter. So you can't just go in there and click on this and just change the value. It always has to change the actual feature as well. Unless, like I said earlier, we're working with nominal values. This is so close to the nominal, you would draw this at 2 inches and you would leave it right there. And then you would apply the tolerance because nominally it's a 2-inch dimension. Here, the hole physically changed from a 3/8 inch diameter to plus a 32nd. You have to draw the new hole size and re-put in the dimension. Okay, I know, you just do. That's called, when you update it and somebody else wants to use it later on, you created good geometry. All right, if you don't do that, that's called fudging dimensions, and that's illegal. Like, seriously. And you're going to be that person that when somebody pulls up your drawing, they're like, oh no, now I got to check everything. There's that person in the, there's 1 or 2 when you pull up, and they may or may not still be at the company, but there are those. You see you see the initials and you're like, oh man, I might as well start over. And it's really true. You don't want to be that person. Okay. You're graduating from WCTC. You're getting good instruction. All right. You want to be, oh, cool. I'm pulling up Tyler's drawing. I know it's good. Now I don't even have to check anything. Seriously, you want to be that person. So anyway, so make sure that your geometry matches any changes that you make as well. Okay. Now, the last part of this is add a revision level to document all this. Now, you would only add an A revision level, but then you would list the items that are there. So when you change your hole here, this is going to be a revision level A by the actual value. And then you're going to go up here and you're going to have an A, and you're going to put in 2 inch, or was 2 inches, and then was 3/8 of an inch. Okay. Counterbore or through hole or whatever. You know, you don't have to go into a ton of detail. Try to keep it brief. And then you're going to add a date over here. And then you're going to, you know, put these down here to add that revision level. And then make sure you put the A with a circle by each dimension that is affected. Okay. And then the date. Questions? Yes.
For the, we're specifying the depth of the counterboard to always see the collar face. Is that just saying that you want the very top of the collar to always meet the bottom of the counterboard?
On this case, yes. Yes. I want this surface right here and this surface need to be in contact at all times with this surface and this surface. We don't want it to bottom out on this.
All right.
Yep. Oh, so that's going to be another revision. That'll be an A. Thank you for reminding me of that. Yes.
Can you put in the A or whatever letter, could it be the same size as the rest of the better?
Yes, absolutely. All text on a drawing has to be the exact same size and font. Absolutely. So yes, it's going to be like putting a note in place. Thank you for asking that. Yes.
For doing that, is it just doing text and letter A and stuff?
Exactly. And make sure you keep the circle on the dimension layer as well, so that it's not like an object layer circle. I'll show you what my drawings look like with the update, so you can get an idea of what that looks like. Any other really good questions? All right, then there's one last drawing I want to look at. The third drawing is this one right here. Okay, so here my update is specify a standard clearance hole size for the 1/2 inch diameter holes. So there's 1, 2, 3, 4 when we look at the right side view here. So the side views are here, and then we can see the side views up there as well. And it says what we want to do is we want to change those to be a clearance hole for a 1/2-13 UNC socket head cap screw. So in this case, the nominal value is a diameter of 0.5, right? Maximum. So to get its clearance hole size, get its standard clearance hole size, what am I going to do, Tyler? I'm going to add what? 1/32 of an inch, okay, for that diameter. And then I'm going to change this diameter. This is going to be my revision A. I'm going to change that diameter to be a 32nd larger, draw it to its correct size, and then update it in all of the views. Okay, and it has to be to the new size, and it has to be dimensioned. And then you're going to put your revision level up here. All right, so let's look at what the drawings are gonna look like. I've been kind of marking up here a little bit, so let's look at what the drawings are gonna look like. So, let me go to AutoCAD. All right, and I'm gonna open up, for instance, the collar. So the collar key, open. Now, you are gonna remove the note that has to do with the update. Take that off. You're gonna remove that, all right? And then what you're gonna do is you're gonna extend these lines. You're not going to explode the block. All you're gonna do is you're gonna extend. So you're gonna be on your dimension layer line. You're gonna do your lines, and you can select the endpoints of these lines and make them, you know, vertical and horizontal. Now, I didn't measure these off specifically, but as Tyler said earlier, notice that my text size matches the text size on the drawing, okay? So these have to match. This can't be small. This can't be larger. It has to be the same. And then you just add the depth here, you know, a line there to be, you know, within that. Don't make them, you know, make enough room so it looks like it's got enough room there. And it's that simple. Now, once I put my A in place, I put it right by the dimension that I chose to affect, okay? The one that I changed, and there it is, okay? And then just make sure that they're on the dimension layer. Now, I'm going to tell you, if you don't have your dimensions set up properly, you're going to struggle with some of this stuff, because when you have, for instance, the scale is in here, as we were talking about, you know, last week, and I've been correcting some of the dimensioning that's been coming in, you're having to change a lot of settings to get things to look right. Okay. And I'm kind of going back and saying, you know what, I'm taking some points off if you don't have it set up properly. So what I did do is, if you need to, now these are set up properly, they should be okay for you. The only thing that you might have to do when you go into annotate, you'll notice that you'll be able to select when you put your text in place, you'll be able to select the proper size. Sometimes it defaults to that 0.2, which isn't correct, but then the other sizes will come up when you select that text. But what I want to point out is I did add to module number 5, and this is where we talked about it. That's where I kind of kept it. I'm going to go back to module number 5. If you need to update your dimension style manager, I created a handout for you. So just as a review, because I know some of you haven't been going back and following along with the video, and I guess that's your choice, but I did make a handout on the step-by-step process. I think this is like 11-page handout on how to set them up for the different styles for English and for metric. So hopefully this will help you to understand what needs to be done. Okay, so if you need to reference that, that's there now. But then let's look at another part. Let's look at the base plate, for instance. Okay, so let me pull up. You're going to remove this note, and then you're going to update the 1/2-inch diameter holes. So if I go here, so now notice that by the 4 1/2-inch diameter holes, I now have a new dimension based on adding a 32nd of an inch. I redrew them. This is an actual dimension. This is not a note. I didn't just change the size of the dimension. You could, but guess what I'm going to do when I pull these up? I'm going to check the actual size of the hole. So it won't go far, and you're going to have to end up doing it anyway. All right. So, so make sure that you update the size of the hole, and then I check it in the side views as well to make sure that they're updated. And then lastly, putting the revision level up here. Yes.
A with circle, do you just use a text box and then an actual just circle?
Exactly. Yeah. So this was just a regular circle, and that was a piece of text. Yeah. Yeah. There is no like little icon for that. Yeah. Yeah. It's just text with a circle. And then keep both on the dimension layer as well as, you know, the lines here for this. If you don't, then like I said, if they're an object line layer, then they're going to be thick like the rest of the part, and we don't want that. It's considered text, you know, even the lines. And then our last one, file open, our third one, let me see here. bearing, right? This one. Oh, I want the key, that's why. I want the key, the bearing key, there we go. And then this one, ignore, okay? Here, notice that we, changed, there was a couple more changes here. And then again, the A's have to be by them. I took the node off for the instructions down in the corner. That's not there anymore, okay? So make sure that you, update these appropriately. Any questions? So your assignment, let's go look back at module number 7. Module number 7, the shaft support revisions is pulling up each one of those individual drawings, making the revisions, and then uploading the files to this Dropbox. Okay, the AutoCAD files themselves, the DWGs. Yes.
For changing the 0.25 for making sure that it
Mhm.
always
Yeah.
fits correctly.
Yes.
Would we actually have to change the length of that?
Yes. Yes, yes. Good question. So for instance, the question was asked, do we have to change the actual depth here? If you change that from 0.25 to something else, yes, you actually do, because then what's going to happen, this is probably going to have to be deeper. And then the crosshatch is going to interfere. So you have to actually change each and every one of these. Yes, it takes time, but guess what? That's going to get it to a place where it's good geometry and it's properly drawn to the dimensions. We're not fudging anything. Okay. If I see fudge dimensions, it's a 0. I don't even know. That's like crossing a line. You can't do that. All right. So if I don't see the diameters, updated, if I don't see this dimension, that's going to be the actual value. Don't look at the number that's there. That's a value that you can use, but it's, you whatever. Okay. But, it has to be drawn to the proper dimension. If it's not, it's a 0. Like even if there's like 3 things you got to change on there, I'm giving you a 0 because you fudged a dimension. All right. That's like game over. Can't do that. That's bad business. You're not going to be that person. Okay. Now I can see that there are a number of people, even in my class here, that are now just focused on finishing that assignment. That's okay. But if I mention anything else about it, if I mention anything else going forward in class here that's important for assignments that are coming up, you're going to miss it. Okay. So, so resist that urge to just jump to the homework. I understand you want to have as much free time as possible, but there's plenty of time to work on that stuff. And then when you're handing things in and I'm marking things off and you're asking me, well, I didn't know that, it was because you're not listening. Okay. Or you're not getting the information, or you're not focusing when you need to. So, so make sure that you're with me when you need to be with me. Any questions then on this assignment? So you're starting with drawings. Okay. You're pulling them up and you're making the changes. You're removing any references to those changes and you're resubmitting with proper revisions and proper updates using the values that we just talked about. So we kind of walked through that, at least the numbers and what to do, through this discussion. Okay. So any questions at all on the shaft support revisions assignment? It's worth 30 points, so about 10 points for each one of the drawings. Okay. And that. All right. So if that's the case, then I'm going to stop recording.